Hi, my name is Hannah Zlotnick, and I am a PhD candidate at the University of Pennsylvania within the Department of Bioengineering, and I'm also a program specialist for the Perry Initiative. Today, I am excited to present to you a case study entitled Engineering Articular Cartilage with Magnetic Fields. So I'll start off with a brief introduction to articular cartilage. Articular cartilage is the joint lining tissue found at the ends of your bones in each of your articulating joints. As you can see in this schematic, each of these joints has a unique geometry. If we zoom in on a histological section of articular cartilage, you can better appreciate how this tissue integrates with the underlying bone. And this integration provides the tissue with unique resistance to shear forces. In healthy articular cartilage, there is a gradient in cell number from the superficial or top zone of the tissue to the deep zone or bottom of the tissue where cartilage integrates with bone. In general, there is a higher cell number in the superficial zone and a lower cell number in the deep zone. However, when this tissue is injured or eventually becomes diseased, as you can see in this image of a focal cartilage lesion, there is a general loss of structure, mechanical properties, and overall function of this tissue. And over time, this may lead to osteoarthritis, which limits the mobility of millions of Americans. So how do surgeons fix cartilage lesions to prevent disease and osteoarthritis? The first option is to simply remove the damaged tissue in a process known as chondroplasty or debridement. And this procedure is typically done arthroscopically through small incisions in the knee. Next, the surgeon may repair the cartilage defect by stimulating endogenous healing. This is typically done through a procedure known as microfracture, where the surgeon uses a conical tipped awl to puncture the subchondral bone and release bone marrow elements into the cartilage defect to promote healing. The third option is to replace the damaged cartilage with healthy cartilage that may be taken from a non-load-bearing portion of the joint, engineered cartilage from a laboratory, or a cartilage-like material. And these procedures are known as osteochondral autograft transfer and matrix-induced autologous chondrocyte implantation, or MACI. As an engineer, I am particularly interested in improving cartilage tissue engineering approaches because engineered cartilage grafts have the potential to mimic native tissue, and they provide an alternative tissue source when healthy cartilage grafts are in short supply. In engineering articular cartilage, we must first think, what is essential to include in this tissue? Well, what's in articular cartilage? First, we have chondrocytes, which are the primary cell source resident in the tissue. These cells deposit extracellular matrix, including collagen type 2 and proteoglycans. Proteoglycans are negatively charged molecules which provide the tissue with its compressive resistance. We must also not forget that articular cartilage has a high percentage of water, which also relates to its unique mechanical properties. On the most basic level, it is essential to include cells, or chondrocytes, and some material to surround these cells and allow them to deposit extracellular matrix. Hydrogels are made of a large percentage water and commonly used as this material to surround the cells. Hydrogels are a liquid in their initial state and are able to be cross-linked to eventually form a solid three-dimensional tissue when cells are encapsulated within them. The question then arises of how do we assemble these building blocks to form cartilage? Can we randomly mix them? To guide the assembly of our engineered tissues, we drew inspiration from the human body, where cell templates lead to heterogeneous tissues, and tissue structure and mechanics loop back and impact further cell activity. The cell arrangement in articular cartilage can be defined as a gradient where the superficial zone has a higher number of cells and the deep zone has a lower number of cells. For our study, we were very interested in mimicking this gradient in our engineered tissues. The overall goal of our study was to control cell positioning within a hydrogel and capture these positions without harming the cells to engineer cartilage. To achieve this goal, we decided to use magnetic fields. We know that iron objects or magnetic objects can be attracted to an underlying magnet. And also, non-magnetic objects surrounded by a magnetic solution can be repulsed from an underlying magnet. We implemented this concept of magnetic repulsion to create cell gradients within hydrogels. Here, the cells are the non-magnetic objects of interest, and they're suspended within a magnetic hydrogel precursor solution. This solution is a liquid to facilitate patterning and turns to a solid to then lock in cell positions. To carry out this research project, we assembled an interdisciplinary team including engineers, physicists, and an orthopedic surgeon. This included myself and another graduate student, Andy Clark, 3 professors, Dr. Robert Mock, Dr. Shumei Chang, and Dr. Sarah Goldbrand, and also Dr. James Carey, the director of the Penn Center for Cartilage Repair. This interdisciplinary team led to the successful completion of this project. So how exactly did we create cell patterns within hydrogels using magnetic fields? Well, first we developed a cross-linkable solution including a hyaluronic acid-based hydrogel and crosslinker, living cells, and the magneto-responsive fluid gadodiamide. We injected this cross-linkable solution inside of a mold on top of a glass slide and nearby a permanent magnet. Over time, the cells moved away from the nearby permanent magnet, as you can see in this video. After achieving the gradient of interest, we exposed the material to a UV light to cross-link the gel and lock in cell positions. After streamlining our fabrication process, we moved on to assess the cell gradients that formed in our magneto pattern tissues. The first step here was to make engineered cartilage tissues with different exposure times to the magnetic field to create different gradients. We then cut the tissues in half, fluorescently labeled the cells, and imaged the cut plane on a microscope. Here you can see representative images from different engineered cartilage tissues that were exposed to a magnetic field for 0 minutes, 2 minutes, 5 minutes, or 10 minutes. You can see that with increasing magnetic field exposure, the cells labeled in cyan moved upward away from the deep zone of the tissue. Moving forward, the next stage in our study was to check the overall health of our tissues. To do this, we first looked at cell viability, where live cells are labeled in green and dead cells are labeled in red. We subsequently imaged these stained cells on the microscope. Our images here show that with increasing exposure to the magnetic field, there were similar amounts of live and dead cells, with mostly live cells throughout the depth of the constructs and a few dead cells at the top of the constructs. Next, we looked to ensure that the cells were happy, and to do this, we performed a metabolic assessment using an assay called the Alamar Blue assay. Here, we looked at construct metabolism for each of the magnetic field exposure times and tracked this cell metabolic activity over time in culture from 1 day to 42 days. We saw very similar trends in each of these groups, signifying no differences in metabolic activity with increasing exposure to the magnetic field. The last aspect of our study was to culture our engineered cartilage tissues for up to 3 weeks in vitro. We then fixed these samples and sectioned them to create thin slices of our tissues that we could then stain for glycosaminoglycans. The staining here shows that with increasing exposure to the magnetic field in this 3 condition, there's less staining in the bottom of the constructs where there were less cells, as we would expect. So, what's next for our magneto pattern cartilage? At the moment, we are in the in vitro lab testing portion of the project. However, we are soon moving forward to large animal studies in mini pigs. This is an intermediate step before our tissues can make it to the clinic. Now, how can you get involved in this type of research or other medical research in the orthopedic field? As an undergraduate, there are many paid summer research opportunities. Listed here are some specifically at the University of Pennsylvania. I encourage you to check these out if you qualify. If you're a high school student, I have also included a link to various high school programs at Penn as well. In conclusion, I would like to thank you for listening to this presentation and also thank the interdisciplinary team of bioengineers, physicists, and surgeons across the University of Pennsylvania, the VA Medical Center, and Bryn Mawr College who came together to support this project. If you're interested in hearing more, I've included the paper link on this slide. Please check it out.